The industry standard for evaluating AI efficiency is the price per 1 million raw tokens. This metric assumes that every token processed has the same economic utility, regardless of how the model is deployed. In reality, autonomous agentic systems create a compounding effect on token exposure, which we identify as the agentic multiplier. A single prompt triggers a cascade. It generates massive tool schemas, re-ingests expanding conversation history, and branches into parallel reasoning paths that may never reach a user. Because this amplification is so high and so variable, optimizing raw token rates while ignoring the execution graph becomes a mathematical trap. You end up subsidizing waste rather than eliminating it. For an organization to scale, the strategic unit of measurement must move from the raw token to the lawful, quality-gated cost per accepted task. To find that true cost, we have to decouple the logical workload from the physical infrastructure processing it. This distinction creates two separate token economies: managed API models provided by vendors and open-weight models that you host yourself. In the managed API economy, you are metered for uncached inputs, creating prompt caches, and discounted rates for reading them. The open-weight economy is different. There are no billing tiers, only physical work. You're limited by GPU seconds spent on prefill and memory bandwidth-heavy decode. Self-hosted systems also internalize operational losses, like idle capacity, failed generations, and control overhead. These require different denominators. For APIs, the goal is the provider bill per accepted task. For self-hosted systems, it is the fully loaded infrastructure cost per accepted task. Applying the wrong denominator to your architecture ensures that your efficiency efforts will never actually reach the balance sheet. If a managed API bill drops, it is tempting to assume the system is doing less redundant work, but that isn't always the case. This baseline represents a workload using 18,000 input tokens and 2,000 output tokens, costing nearly $70,000 per month. A 15% token reduction brings that bill down as expected. However, notice the third bar. The cost drops significantly more, to under $50,000, simply by shifting more inputs into the discounted prompt cache tier. In this final scenario, the system is still processing the exact same number of logical tokens as the middle bar. The workload hasn't shrunk, it's just been reclassified. Mistaking a billing class discount for an architectural efficiency is a dangerous error. It creates a false sense of optimization, while the underlying agentic loops remain bloated and expensive. True orchestration must reduce the actual dependency graph of the application, rather than just exploiting provider rate card tiers. When we shift to open-weight models, we move from the world of rate cards to the world of physical capacity. The bottleneck here is split. The prefill phase is parallel and compute-intensive, while the decode phase is autoregressive and memory bandwidth bound. This chart shows baseline GPU hours and fixed platform costs for 10 million tasks on a self-hosted cluster. When you reduce prefill and decode work, consumed GPU hours drop. But the yellow block representing fixed platform costs, the hardware already purchased, stays exactly the same. This is the denominator paradox. On purchased hardware, using fewer GPU hours doesn't automatically lower your monthly cash outlay. Value is only captured when that newly freed headroom is monetized. You must either scale the resources down, increase your total throughput of accepted tasks, or defer the purchase of next year's hardware expansion. In an open-weight environment, unmonetized GPU headroom is just a paper metric. Value is only realized when elasticity is enacted. Even with the most efficient inference servers, systems still process thousands of tokens that they shouldn't. This happens because of a visibility gap. A local model server sees text fragments, but it has no knowledge of the cross-domain agent state, network conditions, or the terminal goals of the user. As shown here, agentic execution involves constant loops of replaying history and revising plans. Because the local inference server lacks context, it efficiently processes stale reasoning branches or invalid retries, unaware that the downstream work has already failed. Eliminating this waste requires a control layer that sees across domains, connecting agent state to network, storage, and organizational policy. This design is the foundation of the Predictive Tensor Control Plane, or PTCP. PTCP joins task identity with the real-time state of infrastructure and policies. Rather than changing model weights, it coordinates the surrounding dependency graph. By observing these cross-domain boundaries, it preemptively cancels branches or suppresses redundant retries before the GPU queue ever sees them. Structural token reduction only happens when you orchestrate the boundaries that a local inference engine is unable to see. Before deploying a cross-domain control plane, organizations must apply the Amdahl qualification. If your total cost is already dominated by efficient model reasoning, the leverage offered by a control plane may be too small to justify its implementation. Changing how tokens are handled alters the very input the AI receives. This is not a simple billing adjustment. It is a critical production change to the AI's logic. This requires a validation ladder. Any claim of efficiency must be measured against a highly tuned native baseline, labeled A0. Testing must be staged, starting with observe-only telemetry, moving to shadow decision-making, and eventually reversible canary actions with a kill switch. Every optimization is subject to joint non-regression gates. If the task success rate, security posture, or output quality drops even slightly, the optimization is immediately vetoed. A reduction in token count is only valid if it survives this rigorous testing and proves its causality through ablation and removal. There is a cost to being too aggressive. If cutting output tokens prevents an agent from confirming its final state, the optimization has destroyed the utility of the entire task. A topology-aware control plane avoids this risk by safely pruning the execution graph, using stable cache prefixes, and stopping generations the moment a verified terminal state is reached. This approach step-sides the managed API mirage and provides the mechanisms to physically capture the value of open-weight elasticity. The objective is simple: minimize the physical work required to reach a verified outcome. Measuring success by the raw token is a distraction. It ignores the complex reality of how agentic systems actually consume resources. True scale in autonomous AI is achieved strictly by minimizing the fully loaded, quality-gated cost per accepted task.